Welcome to this lecture on multi-agent systems and the 5 orchestration patterns that are reshaping enterprise AI. Before we dive into any code or architecture diagrams, I want to hit you with a number that stopped the entire industry in its tracks. Gartner reported a staggering 1,445% increase in enterprise interest and deployment of multi-agent AI systems between 2024 and 2025. Let that sink in for a moment. Nearly 15 times the attention in a single year. This is not a gradual trend, this is a category explosion. Companies that were experimenting with single LLM API calls just 12 months ago are now building coordinated fleets of specialized AI agents. The question is no longer whether your organization will adopt multi-agent systems. The question is whether you will understand them deeply enough to architect them correctly. That is exactly what this lecture series is designed to answer. So why are single agents simply not enough? Imagine you ask one brilliant engineer to simultaneously write production code, review that same code for security vulnerabilities, run the test suite, write documentation, and coordinate with 3 external APIs, all at once, without losing context. That engineer would fail. Not because they lack skill, but because the cognitive load and parallel demands exceed what any single process can reliably handle. Single-agent architecture face exactly the same ceiling. A single LLM call has a fixed context window, no true parallelism, no specialization, and catastrophic failure when one step goes wrong. Multi-agent systems solve this by distributing work across specialized agents. One plans, one executes, one verifies, one handles tool calls. Each agent is focused, bounded, and replaceable. The result is a system that is more reliable, more scalable, and dramatically more capable than any single agent could ever be. Let us zoom out and look at this as an industry timeline. The journey from simple LLM API calls to fully agentic pipelines happened faster than almost anyone predicted. In 2020 and 2021, the dominant pattern was prompt engineering. Teams were crafting clever single prompts to extract maximum value from GPT-3. By 2022, we saw the rise of chain of thought and sequential LLM pipelines. Tools like LangChain emerged to help string multi-calls together. In 2023, the concept of autonomous agents exploded into mainstream awareness. React, Baby AI, AutoGPT demonstrated that LLMs could plan and act in loops. And now, in 2024 and 2025, the industry has matured past single-agent experiments into structured multi-agent orchestration. Production systems where specialized agents collaborate under defined architectural patterns. This is where we are today, and this is exactly what you are here to master. Now that you understand why multi-agent systems are dominating the enterprise AI conversation, let us map out exactly what this lecture series will teach you. At the center of everything is a single question. Given a complex AI task, which orchestration pattern do I use? We will cover 5 fundamental patterns that together as the full spectrum of production use cases. React, reasoning, and acting in interleaved loops. Second, plan and execute, separating strategic planning from tactical execution. Third, multi-agent collaboration, where peer agents negotiate and coordinate. Fourth, reflection, agents that critique and improve their own outputs. And fifth, tool use orchestration, specialized patterns for managing external tool and API integrations. These 5 patterns are not arbitrary. They emerge directly from the constraints of real production systems. And by the end of this lecture, you will know precisely when and why to reach for each one. Before we go any further, let us be honest about who this lecture is designed for. This is not a beginner's introduction to what a language model is. We are going to move fast and go deep. You should already be comfortable writing Python, not just reading it, but writing production quality functions and classes. You should have hands-on experience calling LLM APIs, whether that is OpenAI, Anthropic, or an open source equivalent. Familiarity with LangChain or LangGraph is strongly recommended. We will reference their abstractions throughout the lecture. If you have built at least one end-to-end AI application, even a simple chatbot or RAG pipeline, you are in the right place. If you are brand new to LLMs entirely, I would recommend pausing here and completing a foundational LLM course first. For everyone else, you are exactly the audience this content was built for. Here is the meta skill that separates good AI engineers from great ones. Knowing which pattern to use before you write a single line of code. Throughout this lecture, we will be building a pattern selection decision tree, a practical framework that maps your task characteristics to right orchestration architecture. The decision tree branches on questions like, does the task require dynamic tool calls at runtime? Does it need iterative self-correction? Is parallelism beneficial or harmful for this workflow? Are there multiple distinct expert domains involved? By Chapter 6, you will have a complete, printable decision framework you can apply to any real-world multi-agent design challenge. Every pattern we cover will add a new branch to this tree. Think of it as the deliverable you are building alongside the lecture content. Let us start building it now, beginning in Chapter 2 with the foundational mechanics of how multi-agent orchestration actually works under the hood. In the previous chapter, we explored why multi-agent systems are exploding in popularity right now. Before we dive into specific orchestration patterns, we need to build a rock-solid conceptual foundation. So let's start with the most fundamental question. What exactly is an AI agent? At its core, an agent is not just a chatbot that responds to prompts. An agent is an autonomous computational unit built around a large language model. The LLM acts as the reasoning brain, combined with memory to retain context, tools to act on the world, and most importantly, a control loop that lets it perceive its environment, reason about the situation, decide on an action, execute that action, and then observe the result. This perception-action loop is what separates an agent from a simple prompt response system. The agent keeps cycling through this loop until it determines the task is complete. Think of it like the difference between a calculator and a software engineer. The calculator just computes what you ask, but the engineer understands the goal, breaks it down, uses tools, checks results, and iterates. That autonomy, the ability to make sequential decisions without human intervention at every step, is the defining characteristic of an AI agent. Now that we know what an agent is conceptually, let's zoom in on its internal architecture, the layered stack of components that make an agent actually function. Picture this as a technology stack, just like you'd describe a web application. At the very top, you have the LLM itself. Models like GPT-4i, Claude 3.5, or Gemini 1.5. This is the inference engine doing all the reasoning. Directly beneath that sits the tool layer. These are callable functions the LLM can invoke. Things like web search, code execution, database queries, or external API calls. Tools are how the agent's outside its own context window and touches the real world. Below tools, we have short-term memory. This is essentially the active context window of the conversation, storing the current state, recent observations, and the ongoing chain of thought. Think of it as working memory. And at the foundation, we have long-term memory, typically implemented as a vector store or a key-value database. Long-term memory persists information across sessions, learned facts, user preferences, episodic records of past tasks. This is what allows an agent to remember that last Tuesday you asked it to monitor a specific stock price, even in an entirely new session. Understanding this stack is critical because when you design orchestration patterns, you're essentially deciding how multiple instances of this stack interact with each other. With the single agent stack clear in our minds, we can now introduce the most important relationship in multi-agent systems, the orchestrator and the subagent. This is the architectural backbone that every orchestration pattern built on. An orchestrator, sometimes called a supervisor agent, is an agent whose primary job is not to solve the problem directly, but to coordinate other agents that do the actual work. When a complex task arrives, the orchestrator decomposes it into subtasks, delegates each subtask to a specialized subagent, collects the results through message passing, and synthesizes those results into a final output. The subagents are typically specialized. One might be a research agent with access to web search tools, and there might be a coding agent with a Python execution environment, and a third might be a data analysis agent connected to a database. Message passing is the communication protocol between orchestrator and subagents. It defines what information travels between them, in what format, and in what order. This could be as simple as a structured JSON payload or as sophisticated as a typed event stream. The key design decision you always face is, how much autonomy does each subagent have? Does the orchestrator micromanage every step, or does it hand off a goal and trust the subagent to figure out how to achieve it? That fundamental tension shapes everything we'll cover in the 5 patterns ahead. Now that we understand the building blocks, agents, tools, memory, and the orchestrator-subagent relationship, we can ask a deeper question. What exactly makes something an orchestration pattern? In software engineering, a design pattern is a reusable solution to a commonly occurring problem in a given context. Orchestration patterns are the same idea applied to multi-agent coordination. Specifically, an orchestration pattern is defined by 3 things. First, control flow, the rules that determine which agent runs when, whether execution is sequential or parallel, and how branching decisions are made. Second, state management, how the shared understanding of the task's progress is stored, updated, and made accessible to all participating agents. And third, the communication contract, the agreed-upon format and protocol for messages passed between agents. This includes what data is included, what schemas are expected, and how errors and retries are handled. When these 3 dimensions are well-defined and repeatable, you have a pattern. When they're ad hoc and inconsistent, you have spaghetti. The 5 patterns we'll cover in this lecture each represent a distinct combination of control flow style, state management strategy, and communication contract. And each combination is suited to different class of problems. When it comes to actually implementing these orchestration patterns in code, 2 frameworks dominate the landscape today: LangChain and LangGraph. It's worth understanding how they differ because they reflect 2 fundamentally different philosophies about orchestration. LangChain, the original framework, uses a chain-based model. You compose agents and tools into linear or branching chains of calls. It's excellent for sequential workflows and has a rich ecosystem of pre-built integrations. However, as workflows become more complex, with cycles, loops, or dynamic routing, LangChain chains become hard to manage. This is exactly why LangGraph was introduced. LangGraph treats your multi-agent workflow as an explicit directed graph, where nodes are agents or functions and edges represent transitions between them. State is a first-class citizen passed between nodes. This graph-based model makes it dramatically easier to express patterns like loops, conditional rerouting, and parallel fan-out and fan-in. For example, in LangGraph, you can define a supervisor node that inspects the current state and dynamically routes to whichever subagent is most appropriate, and then have that subagent's output back into the supervisor for another decision cycle. This kind of dynamic orchestration is cumbersome in LangChain but natural in LangGraph. For the patterns we'll cover in this lecture, LangGraph will be our primary implementation vehicle, though the concepts apply regardless of framework. Before we jump into the 5 specific patterns in the next chapters, let's close this foundational section with a crucial practical reality check. Every orchestration pattern involves trade-offs, and there is no universally best choice. To make intelligent decisions in your own projects, you need to understand 4 dimensions: latency, cost, complexity, and reliability. Simple sequential patterns have low latency variance and are easy to debug, but they can't parallelize work and may be slow for large tasks. Parallel patterns dramatically reduce end-to-end latency by running subagents simultaneously, but they multiply your LLM API costs and introduce synchronization challenges. Highly dynamic patterns that route decisions at runtime are extremely flexible, but they add architectural complexity and make failures harder to trace. And reliability, your ability to recover from a single agent failure without losing the entire task, varies significantly based on how state is managed and whether the pattern supports checkpointing and retry logic. This table gives you a high-level orientation across pattern categories. As we cover each of the 5 patterns in the coming chapters, keep these 4 axes in mind. They'll help you map each pattern to the right real-world use case. And that practical judgment is ultimately what separates a good multi-agent architect from someone who just knows the theory. Welcome back. In the previous chapter, we established the foundational principles of multi-agent orchestration, how agents coordinate, communicate, and share state. Now we are going to get hands-on with actual patterns. We start with pattern 1, React. React stands for reasoning and acting, and it was introduced by Yao and colleagues in their 2022 paper published alongside Google Brain. The core insight is elegantly simple. Instead of having an LLM either think silently or act blindly, you interleave explicit reasoning traces with tool actions. The agent produces a thought, articulating what it knows and what it needs, then takes an action using a tool, and finally receives an observation from that tool. This 3-phase loop repeats until the agent reaches a final answer. Think of it like a scientist writing in a lab notebook. Jot down your hypothesis, run the experiment, record the result, then update your hypothesis. That cycle is exactly what React formalizes for language model agents. Let us walk through the React execution cycle with a concrete example. Suppose the user asks, "What is the current CEO of OpenAI and what university did they attend?" The agent begins with a thought, "I need to find who the current CEO of OpenAI is. I should search for this." It then fires an action, calling the search tool with the query current CEO of OpenAI 2024. The observation comes back, "Sam Altman is the CEO of OpenAI." The agent writes a second thought, "Now I know the CEO is Sam Altman. I need to find which university he attended." A second action fires, "Search for Sam Altman University education." The observation returns, "Sam Altman attended Stanford University but dropped out." The agent's final thought is, "I now have both pieces of information," and it outputs the final answer. Notice the scratchpad. Every thought and observation is appended to the prompt context. This is how the agent maintains memory across the loop without any external storage. Now let us see how this looks in actual Python code using LangChain. LangChain provides the agent executor class, which handles the React loop for you automatically. You first define your tools. Here we use a DuckDuckGo search tool. Then you initialize the agent using the initializeAgent function, passing in the tool list, the LLM, and specifying the agent type as zero-shot React description. This agent type tells LangChain to use the React prompting format. Finally, you call agent.run with your question, and LangChain internally manages the thought, action, observation loop until a final answer is produced. The verbose equals true flag is extremely useful during development. It prints the full scratchpad so you can see every reasoning step and tool call. In production, you would set this to false. Notice how little code this takes. The orchestration complexity is handled by the framework, letting you focus on defining the right tools and prompts. So when should you actually reach for React? And when is it the wrong tool? React is ideal for interactive question answering tasks that require one or tool lookups. It works great for customer support bots, research assistants doing lightweight fact-finding, and any scenario where the task is relatively self-contained and does not require coordinating multiple agents simultaneously. However, there are clear red flags. If your task involves more than 5 or 6 sequential steps, the scratchpad grows enormous, and LLMs start losing track of earlier observations, a phenomenon called context drift. If the task requires parallel execution of subtasks, React is fundamentally sequential and will be slow. And if failure in one step should trigger a complete replan, rather than just retrying, you need a more sophisticated pattern. When you hit those red flags, that is the signal to our next pattern, plan and execute, which we cover right now. Now we move to pattern 2, plan and execute. This pattern directly addresses the limitations of React we just discussed. The core idea is a clean separation of concerns between two distinct roles. The planner agent, typically a powerful LLM like GPT-4, receives the high-level goal and produces a structured, ordered list of subtasks before any execution begins. The executor agents, which can be simpler, cheaper models, then carry out each subtask one by one, or potentially in parallel. Think of it like building a house. You do not hire a contractor and tell them to figure it out as they go. You first work with an architect to produce a complete blueprint, then you hand that blueprint to specialized tradespeople, electricians, plumbers, carpenters, who each execute their defined scope. Plan and execute brings that same engineering discipline to AI agent systems. The planner thinks globally. The executors act locally. Let us trace through the full plan and execute lifecycle with a realistic example. Suppose the goal is, research the top 3 cloud providers and write a comparison report. Step 1. The planner agent receives this goal and generates a structured plan. For example, Step 1, search for AWS share and key services. Step 2, search for Azure market share and key services. Step 3, search for GCP market share and key services. Step 4, synthesize findings into a comparison table. Step 5, write the executive summary. The executor then runs each step sequentially. Now here is the critical part, replanning. If Step 2 fails because the search API is unavailable, the system does not crash. Instead, the result is fed back to the planner, which revises the remaining plan, perhaps substituting a different data source for Step 2, and execution continues from there. This feedback loop between executor results and the planner is what makes plan and execute robust for complex, multi-step workflows. Let us look at the Python implementation. LangChain provides a plan and execute class in its experimental agents module. You define a planner using load chat planner. This wraps a powerful LLM with the planning prompt. Then you define an executor using load agent executor. This is the React-style agent that will execute individual steps. Notice something important here. The executor is itself a React agent. Plan and execute actually composes on top of pattern 1. The planner handles the macro-level decomposition, while each executor step uses the micro-level React loop. Finally, you combine them with plan and execute and call run with your goal. The system will print the generated plan first, then show each step being executed. This composability is a key architectural insight. Advanced orchestration patterns often build on simpler ones, rather than replacing them. Now let us put both patterns side by side to crystallize when you should choose one over the other. React is best when the task is short, interactive, and emergent, meaning you cannot predict all the steps up front. It has low latency and low overhead, making it perfect for conversational interfaces. Plan and execute wins when the task is long, complex, and structured, where knowing the full plan in advance gives you better control, error recovery, and parallelization opportunities. The key trade-off is predictability versus flexibility. React adapts fluidly, but can lose its way on long tasks. Plan and execute is structured and auditable, but adds the overhead of an upfront planning call. In practice, many production systems use plan and execute for the outer workflow and embed React agents as the executors for individual steps, exactly as we saw in the code. In the next chapter, we will explore patterns 3, 4, and 5, collaborative multi-agent networks, self-reflection loops, and structured tool use agents. Welcome to Chapter 4. In the previous chapter, we covered React and plan and execute. Powerful patterns for single-agent reasoning. Now we step into the world of agent teams. Pattern 3 is multi-agent collaboration. Instead of one agent doing everything, you define specialized worker agents, each with a focused role and a supervisor agent that coordinates them. Think of like a software engineering team. One agent researches, another writes code, another reviews. The supervisor reads the task, decides which worker is best suited, and routes the job accordingly. This division of labor dramatically reduces cognitive overload on any single agent and improves overall output quality. The key concept is role assignment. Each agent has a clearly defined responsibility, and the supervisor acts as an intelligent dispatcher. To implement multi-agent collaboration in code, we use LangGraph, which models the entire system as a directed graph. Each agent becomes a node in the graph. The supervisor is also a node, but instead of doing domain work, it reads the current state and emits a routing decision. LangGraph supports conditional edges. After the supervisor node executes, a conditional edge function examines the supervisor's output, then dynamically selects which worker node to activate next. All agents communicate through a shared message state, a structured object that holds the conversation history, task description, and intermediate results. When a worker finishes, control flows back to the supervisor, which either routes to another worker or signals that the task is complete. This graph-based model, the collaboration topology explicit and easy to visualize. Let us look at the actual Python code. We first define a type predict agent state that holds a list of messages, and a next field indicating which agent runs next. We build two worker chains, a researcher chain and a coder chain, each backed by a chat OpenAI model with a specialized system prompt. The supervisor node is a chain that receives the current messages and outputs a JSON object with a next field set to either researcher, coder, or finish. We then construct a state graph, add all three nodes, and wire conditional edges from the supervisor using a router function that simply reads state bracket, next bracket. Finally, we call graph.onPile and invoke it with the initial user message. The graph will cycle through supervisor and worker nodes autonomously until the supervisor decides the task is done. This compact structure is all you need to run a two-worker collaborative agent team. Pattern 4 is the reflection pattern, and it is one of the most powerful techniques for improving output quality without human intervention. The core idea is simple. You separate the act of generation from the act of evaluation. A generator agent produces an initial response, a draft essay, a piece of code, or a plan. A critic agent then receives that output and evaluates it against a set of criteria: correctness, completeness, clarity, or whatever quality dimensions matter for your use case. The critic returns structured feedback. The generator then revises its output using that feedback. This cycle repeats until the critic is satisfied or a maximum iteration count is reached. Think of it like a writer and an editor working together in a tight loop. The reflection pattern is especially valuable in tasks where quality is hard to verify externally, but internal consistency can be judged by another LLM call. Let us walk through the reflection loop step by step. First, the generator receives the original user task and produces an initial draft. Second, the critic receives both the original task and the draft, then outputs a structured evaluation. This might include a score, a list of issues, and specific improvement suggestions. Third, the generator receives the original task plus the critic's feedback and produces a revised draft. Fourth, the critic evaluates the revision again. This cycle continues, and at each critic step, we check the stopping condition. There are two common stopping conditions. The critic explicitly signals approval for returning an unapprove flag, or we have reached the maximum number of iterations, typically 3 to 5, to prevent infinite loops and control API costs. The quality of the critic prompt is critical. It must be specific enough to give actionable guidance, not just generic comments like needs improvement. Here is a Python implementation of the reflection pattern. We define two LangChain chains, generator chain and critic chain. Generator chain uses a chat prompt template that takes the task and optional feedback as input. The critic chain takes the task and the current draft and returns a structured response, a numeric score from 1 to 10 and a feedback string. In the main reflection loop, we start with no feedback and call generate to get an initial draft. We then enter a while loop that runs up to max iterations, calling critique on each draft. If the score is 8 or above, we break out of the loop early. That is our quality threshold. Otherwise, we pass the feedback back to generate for a revision. After the loop, we return the best draft. Notice how clean this structure is: 2 chains, 1 loop, 1 stopping condition. This pattern is especially effective for creative writing, code generation, and structured data extraction tasks. Our fifth and final pattern is tool use, the capability that transforms a language model from a text predictor into an active agent that can interact with the world. Without tools, an LLM is limited to its training knowledge. With tools, it can query live databases, call REST APIs, run Python code, search the web, read files, and much more. The tool use pattern works through function calling. The LLM is given a registry of available tools, each described by a JSON schema specifying its name, description, and parameters. When the LLM determines that a tool would help answer the user's query, it generates a structured tool call rather than a plain text response. The host application intercepts this call, executes the actual tool function, and returns the result to the LLM, which then incorporates it into its final answer. This pattern is foundational. In fact, React, which we saw in Chapter 3, is essentially a specific implementation of the tool use pattern, combined with chain-of-thought reasoning. Let us trace the exact execution flow of the tool use pattern. Step 1 is tool schema definition. For every tool, you write a JSON schema describing the function name, a natural language description that helps the LLM decide when to use it, and the parameter types. Step 2 is LLM tool selection. The LLM receives the user message along with the list of tool schemas. Based on the user intent, it decides whether to call a tool, and if so, which one. Step 3 is argument generation. The LLM generates the exact arguments for the tool call in JSON format, respecting the parameter schema. Step 4 is tool execution. Your application code receives the structured tool call, validates the arguments, and executes the actual function. Step 5 is result parsing. The function return value is serialized back as a tool message and appended to the conversation history. The LLM then reads the tool result and generates the final human-readable response. This 5-step cycle can repeat multiple times in a single agent turn if chain tool calls are needed. Now let us write it in Python using LangChain. LangChain provides a tool decorator that makes defining custom tools extremely straightforward. You write a regular Python function with a docstring. LangChain uses the docstring as the tool description for the LLM. In this example, we define a getStockPrice tool that takes a ticker symbol and returns the current price. We also define a calculate tool for arithmetic. We then call bind tools, passing a list of our tool objects. This tells the LLM about the available tools at inference time. We create an agent executor using create tool calling agent from LangChain, passing the bound LLM, our tools list, and a prompt template. Finally, agent executor invoke runs the full tool use loop automatically. The framework handles parsing tool calls, executing functions, and feeding results back to the LLM until a final answer is produced. With this foundation in all 5 patterns, our next chapter will guide you through choosing the right pattern for your specific use case. Welcome back. In the previous chapter, we explored patterns 3, 4, and 5, multi-agent collaboration, reflection, and tool use. Now, critical question every architect faces. Given real problem, which pattern do you actually choose? The answer lies in a structured decision tree. Start by asking, is the task a single, atomic action? If yes, a simple React loop is sufficient. If the task requires multiple steps with upfront planning, move to plan and execute. Next, ask whether output quality is the top priority and self-correction is needed. That points you toward the reflection pattern. If the task is naturally parallelizable across specialized domain, multi-agent collaboration is your answer. Finally, if the task requires dynamic access to external data sources or APIs at runtime, tool use becomes essential, and it can be embedded inside any other pattern. This decision tree is your compass for architectural choices, and memorizing these branch conditions will save you enormous time during system design. Now, in production systems, you rarely deploy a single pattern in isolation. Real-world pipelines are hybrid architectures that combine patterns to address multiple requirements simultaneously. Consider a code generation system. The outer layer might be a multi-agent collaboration graph, where a planner agent, a coder agent, and a reviewer agent each have specialized roles. But inside the reviewer agent, you embed a reflection loop. The reviewer critiques the code, sends feedback, and the coder iterates until quality gates pass. Meanwhile, the coder agent uses tool use to call a code execution sandbox and a documentation lookup API. Another common combination is React plus reflection. The agent acts and observes in a React, but after each major milestone, a reflection step evaluates accumulated progress. The key insight here is that patterns are composable building blocks. Think of them as design patterns in software engineering. You combine them based on the specific quality attributes your system must satisfy: latency, accuracy, cost, and maintainability. Before we move on, let's talk about what not to do, because the most expensive mistakes in multi-agent system design are patterns. The first anti-pattern is over-engineering, applying a complex collaboration graph to a task that a single React loop could handle in milliseconds. Every agent you add introduces latency, token cost, and failure surface. Second is the latency trap. chaining too many sequential reflection loops without setting a maximum iteration count, causing user-facing response times to balloon unpredictably. Third is cost explosion. Tool use agents that call expensive external APIs in tight loops without caching, result deduplication, or rate limiting. Fourth is agent sprawl, creating dozens of narrowly specialized agents with overlapping responsibilities, making the system nearly impossible to debug. The rule of thumb is, start with the simplest pattern that could possibly work, measure its shortcomings empirically, and only then introduce a more complex orchestration layer. Complexity should be earned, not assumed. Let's ground everything we've learned in concrete enterprise scenarios. Looking at our use case mapping table, React, the workhorse behind customer support bots. The agent receives a user query, calls a CRM lookup tool, checks order status, and responds, all in a single reactive loop with no upfront planning needed. Plan and execute shines in research pipelines, where an LLM first decomposes a complex search question into a structured plan, search academic databases, summarize findings, cross-reference sources, then executes each step sequentially. Multi-agent collaboration powers document processing workflows, where parallel agents simultaneously extract entities, classify sentiment, and verify compliance, dramatically reducing end-to-end latency. The reflection pattern is the backbone of automated report generation systems, where a draft is produced and then iteratively critiqued against style guides, factual accuracy checks, and compliance rules until all gates pass. And tool use is universal in financial data analysis agents that need live market feeds, engines, and charting APIs injected dynamically at runtime. Knowing these canonical mappings will help you justify architectural decisions to both engineering teams and business stakeholders. Let's walk through a complete production example that puts theory into practice. An automated code generation pipeline. The entry point is an orchestrator agent that receives a natural language feature request from a developer. Step 1. The planner agent uses plan and execute to decompose the request into subtasks, write unit tests, implement the function, write documentation. Step 2. The coder agent, operating in a tool use pattern, generates the code and invokes a sandboxed code execution tool to verify it compiles and passes basic syntax checks. Step 3. The reflection loop kicks in. A dedicated reviewer agent critiques the code for correctness, security vulnerabilities, and style guide compliance. If the review fails, a structured critique is fed back to the coder agent for revision. This loop continues until the reviewer assigns a passing score or a maximum of 3 iterations is reached. Step 4. A documentation agent runs in parallel via multi-agent collaboration to generate inline comments and a README section simultaneously. The result is a production-ready artifact delivered with multiple quality gates built directly into the pipeline architecture. Building sophisticated multi-agent pipelines is only half the challenge. The other half is knowing what is happening inside them at runtime. This brings us to observability, the practice of making your agent system transparent, traceable, and debuggable in production. The most widely adopted tool in the LangChain ecosystem is Langsmith, which provides end-to-end tracing of every LLM call, tool invocation, and agent decision step in your pipeline. With Langsmith, you can inspect the exact prompt sent to each agent, the raw model output before parsing, the tools called and their responses, and the total token cost per run. For multi-agent systems, specifically, distributed tracing is critical because failures are rarely in a single agent. They emerge from the interaction between agents. Beyond Langsmith, you should also instrument custom metrics: agent success rate per node, average reflection iterations, tool call latency, and cost per pipeline run. These metrics feed into dashboards that let you detect degradation, runaway loops, cost anomalies before they impact users. In the final chapter, we will bring together all 5 patterns into a unified summary and discuss your next steps for hands-on implementation. Welcome to our final chapter. In the previous session, we walked through real-world scenarios and practiced choosing the right orchestration pattern for different problem types. Let's bring everything together. Over the course of this lecture, we covered 5 foundational orchestration patterns for multi-agent systems. First, React, where an agent reasons and acts in a tight interleaved loop, ideal for dynamic, unpredictable tasks. Second, plan and execute, where a planner agent decomposes the goal upfront and an executor carries out each step, best for structured, multi-step workflows. Third, collaboration, multiple specialized agents work in parallel or in sequence, handing off context to each other, perfect for complex pipelines requiring diverse expertise. Fourth, reflection, an agent critiques its own output and iterates toward higher quality, invaluable when accuracy and self-correction matter. And fifth, tool use, agents are equipped with external tools like APIs, databases, and code interpreters, extending their capabilities far beyond language alone. Each pattern is a design primitive. Your real-world systems will often combine two or more of these primitives into a hybrid architecture. Understanding each one individually gives you the vocabulary and the judgment to compose them intelligently. Now let's leave you with a practical decision framework, something you can screenshot and keep on your desk. When you face a new agentic system design, ask yourself these questions in order. 1. Is the task dynamic and unpredictable, requiring real-time reasoning? If yes, start with React. 2. Is the goal clearly decomposable into ordered steps before execution begins? Then plan and execute as your baseline. Does the problem or genuinely different types of expertise, for example, research plus writing plus validation? That's a signal for the collaboration pattern. 4. Is output quality critical, and can you afford multiple iterations to self-correct? Layer in reflection. 5. Does your agent need to interact with the external world, APIs, databases, file systems, or code execution? Tool use is non-negotiable. 6. If two or more of the above are true simultaneously, design a hybrid. Start simple, validate each layer, then compose. Remember, the goal is not to use all 5 patterns, it's to use the right one, or the right combination, for your specific problem. So where do you go from here? The concepts we covered in this lecture are your theoretical foundation, but the real mastery comes from building. Here is a great learning path I recommend. Step 1. Deep dive into LangGraph. LangGraph is currently the most expressive framework for implementing stateful, graph-based multi-agent workflows in Python. Build a React agent from scratch using LangGraph StateGraph API. This will cement your understanding of how agent loops actually work under the hood. Step 2. Explore AutoGen by Microsoft. Auto excels at the collaboration pattern, providing a clean abstraction for multi-agent conversations and role assignment. Try replicating a research and write pipeline using AutoGen's assistant agent and user proxy agent classes. Step 3. Experiment with Crew AI. Crew AI provides a high-level, role-based abstraction that maps almost directly onto the collaboration and plan and execute patterns. It's excellent for rapid prototyping of crew-style agent teams. Step 4. Build a hands-on capstone project. Take a real problem from your domain, whether it's automated code review, research summarization, or customer support triage, and implement it using at least 2 of the 5 patterns in a hybrid architecture. Document your design decisions. That process of justifying your pattern choices is where genuine engineering judgment develops. Let me leave you with a thought that I believe captures exactly where we are in the history of software engineering. We are not simply building smarter chatbots. We are designing systems that can reason, plan, collaborate, reflect, and act autonomously on behalf of humans. The orchestration patterns we studied today are the grammar of this new discipline. Just as object-oriented design gave us reusable, composable software, agentic orchestration patterns give us reusable, composable intelligence. The engineers who internalize these patterns today will be the architects of the systems that define the next decade. If this lecture was valuable to you, please subscribe to the channel, leave a comment sharing which pattern you're most excited to implement, and share this with a colleague who is stepping into the world of agentic AI. The community we build around these ideas is just as important as the code we write. Thank you for learning with me. Now go build something extraordinary.